continuing on with question 2 in the AP 2023 exam, we're looking at these gas molecules of aluminum chloride shown below, and we're told that the AlCl3 has a trigonal planar geometry, and then we need to use these given diagrams to eliminate one of them based on their geometry, and we should be citing VSEPR theory in our answer. So I like to approach VSEPR theory by using, I like these generic formulas. I'm not sure if you guys have seen them in your classes, but for example, when I have something like this AX3, this is going to be a planar trigonal or trigonal planar. And what this generic formula means is I have a central atom A bonded to 3 other atoms, X, and there are no lone electrons on the A. So then all of the bonds spread out evenly. And that's what diagrams 1 and 3 actually show. But they're not necessarily drawn to scale. If I was to draw it to scale, I'm just going to use the letters AX, then I would spread out these bonds evenly. And these X's have these lone pairs on them, lone electron pairs. These bonds will spread out evenly. There's nothing really else pushing them, so they'll spread out equally into this kind of equilateral triangle. So these are 120-degree angles, or this trigonal planar shape. Now, another variation of this generic formula is AX3E. And if I have this configuration, this will be my trigonal pyramidal. And so this E represents lone electrons on the central atom, which is what this diagram number 2 shows. So I know that diagram number 2 can be eliminated. It is not a trigonal planar because of these lone electrons on aluminum that will push away these bonds. That's what this stands for, valence shell electron pair repulsion. So let's write down our answer. Diagram 2 is wrong, can be eliminated. The reason it can be eliminated is because the lone electron pair on aluminum will repel away the chlorine bonds, causing a trigonal pyramidal shape rather than a planar shape. And again, you can use the answer key online to look at the better wording. But essentially when this happens, this trigonal pyramidal shape will look something like this. So this lone pair here is going to push away these bonds into this trigonal pyramidal. So it's kind of like more 3-dimensional, whereas the planar triangle is 2-dimensional. All right, so this will push this away, these bonds, and my atoms here, X. And this has more of a characteristic bonding angle, about 107.5. But you can look up the angles later if you want to study them. All right, now this next question, I've already drawn the diagram because this is actually the answer. It says here, which of the 3 diagrams is the best representation for this AlCl3? Justify our choice using formal charges. I'm just going to do it over there because it's a little too small to draw it on these given diagrams. I eliminated diagram 3, and I'll show you why, because now there's different ways you can do formal charge check. I like to do it this way, where I split the bond in half. So I split this line in half like this. And then when I split the bond, remember the bond is 2 electrons. So I'll put 1 dot there and 1 dot there. And I use the formula, the valence electrons that the atom has. So let's look at the chlorine on the right. This one has 7 valence electrons. In this configuration, there's also 7 dots around it. So I subtract that. And then I get a formal charge here of 0. And that's good. So in a neutral compound like AlCl3, I am striving for formal charges of 0 for all of my atoms. So let's go to the chlorine on the left and do the same thing. Split this in half, put a dot there, put a dot there. Chlorine has 7 valence electrons, and again in this configuration, 7 dots. So I subtract that, and I get a formal charge of 0. And then the chlorine on the top, same, you're going to get the same answer, right? So split this in half, put a dot there, put a dot there. 7 valence electrons minus 7 dots. That gives me 0. And the aluminum has 3 valence electrons. There's 3 dots around it. So it also has a formal charge of 0. So in this answer, diagram 1 is the best because all atoms have a formal charge, I'll just say Fc, of 0, which is what they strive for in a neutral compound. It may differ in a polyatomic. If there's a question like that, I'll show you how, or maybe I'll make another video on that if you're interested. But when you have a neutral atom, all the atoms are striving for a formal charge of 0. Let's move on to the last question in number 2, which is talking about a gas equilibrium. And let's, in the first question, calculate, sorry, not calculate. We just have to write down the Kp expression. So we just have to write the equilibrium expression. Now, this is gases. So what it will be is the pressure of the products, I'll use P for pressure of the products, divided by the pressure of the reactants, raised to their mole ratio. So for this question, Kp will equal the pressure of Al2Cl6 divided by the pressure of AlCl3 squared. That's my equilibrium expression, and it'll show me the ratio of product to reactant at equilibrium. Now, there is a calculation to follow up in question F. So I'm given a particle level diagram of the equilibrium of this reaction up here, and I'm being asked to calculate the value of Kp if the total pressure in the container is 22.1 atmospheres. So we already wrote the formula up there. I'm not going to recopy it, but Kp is going to equal Al2Cl6. That is, no, Al is the white circle, Cl is the shaded in circle. So there's 1, 2, 3. There are 3 Al2, there's 3 product molecules out of, if you count these up, there's 10 compounds. So what I know is that the pressure of the product is going to be 3/10 of 22.1 atmospheres. And I'm going to divide that by the pressure of my reactants, which is going to be, well, 7. So again, AlCl3 is represented by this picture. So 1, 2, 3, 4, 5, 6, 7. So that's represented, the pressure of that reactant is going to be 7/10 of 22.1 atmospheres. But this has to be squared. All right, because we have to use our pressure equilibrium constant. And when you do this calculation, I will get a Kp value of 0.0277. It is unitless. Even though the atmospheres did not cancel out perfectly, our equilibrium constants, they're always unitless. And this answer means that I favor, and you can tell from the diagram as well, but I'm favoring the reactant because my K constant is less than 1. I hope that helps. You can watch the next video if you're interested in the next question. Thank you.